The derivative of exponential is quite a special one. So I'm going to start with really simple examples, but also develop the derivative rule for it even further. So by this point, I assume that you are fluent in most of the derivative rules, such as the chain rule, product rule, and the quotient rule, because they're going to come in handy when you're dealing with the derivative of other functions. So for exponentials, the derivative is actually the exponential itself. It doesn't change. One way to check that is you could graph f of x, and then you can use the function on your graph where you find the derivative at a point, and you'll notice that it will always be the same as the output of the function. So the derivative of e to the power of x is e to the power of x. Now let's do just a simple example. Let's say I have 7e to the power of x, so there's a coefficient. What I can do is split the coefficient from my function. You can do that, just take it out. And what you're going to do is just apply the derivative to e to the power of x. That's something you do already in functions, so in derivatives. So I'm just going to put the coefficient on the side. I'm going to derive e of x and multiply with 7. Well, the derivative of e of x is just e of x, so we're back to the same function. It seems a bit weird, but you'll get used to it in a bit. So we multiply the derivative with the coefficient, and the derivative is just e of x. And we can do the same thing here. You can pause and try it yourself, but it's the same concept. You just split it with from the e of x, and the derivative of e to the power of x is just e to the power of x. Now, we can develop the rule a bit further where we say, well, if the power itself had a coefficient, so let's say k is a constant, so that was a coefficient of the power here, then we can say that the derivative f of x is equal to just k, so you bring the coefficient down, e to the power of kx. So for example, if I have y equals to e, if I have e to the power of 2x, then I can take the coefficient down, and it's going the dy by dx is just going to be 2e to the power of 2x. So the 2 becomes a coefficient now because it was a coefficient here. And notice the e to the power of 2x doesn't change, so you keep it the same. We're back to the same first rule. Again, it seems weird, but you'll get used to it. So let's say I have this function p equals to e to the power of 4x. dp by dx, I'm intentionally using different letters so you get used to the use of different letters, is going to be equal to 4e to the power of, sorry, this is meant to be 4 of x to e to the power of 4x. So it stays the same. And then m is equal to e to the power of 5t, and same thing, dm by dt is going to be 5e to the power of 5t. So any coefficient you have here in the power, we can bring as a coefficient to the function itself, and we keep the exponential as it is. So it's going to stay as e to the power of 2x, e to the power of 4x, e to the power of 5t. Now, let's develop this even further. What if we don't have just a constant? What if we have a whole function? So it's not just k of x, it's a whole lot of things happening to x. So I can define it as a function, u of x. In this case, the derivative is going to be the derivative of u of the power times e to the power of u of x doesn't change. So back to the same e of x, or back to the same rule, it doesn't change. But you have to multiply the derivative, which is technically what we're doing in this step, in this rule, but this last rule kind of makes it all formal. So if I have this, what I'm going to do, dy by dx is going to be the derivative of the power. So the derivative of the power is 6x squared. And then I multiply by the exponential, which doesn't change. It stays as it is. So that's what you do. You make sure you look at your power, you derive it, and you make it a coefficient, and then you keep the exponential the same. Let's look at another example. If I have this, now this is a whole load of mess. And what I'm going to do is I'm going to derive the power, and I'm going to have, and then I'm going to multiply the original exponential. So that's what you're going to get. Now, if you're very fluent in the chain rule, a double chain rule actually, then you are able to derive this in your head really quickly. So what I just did is, if you notice, the power itself is a function inside another function. So you'd have to use the chain rule here. So if you use the chain rule, you derive the power using the chain rule, then you put it as the coefficients, and then you put this here. If you can do it in your head, then you can skip a few minutes of this video. So this is the derivative of the power, and this is the exponential. What I'm going to do on the next slide is actually show how it's done using the chain rule. If you already understand this part, you can skip ahead. So I'm going to take the same exact function and I'm going to do a substitution. We're going to use the chain rule twice. What I'm actually going to do is explain how the chain rule applies in this, that this last rule is actually us using the chain rule. But I'm also going to show how you're going to derive the power, which you should know from other videos. So I'm going to say u is this function, and so y equals to e to the power of u. Now this is what happens when you want to find dy by dx, which is the original derivative. Notice the color coding, this is the black part. I need to first find dy by du, so this, which is just e to the power of u, times du by dx, which is the derivative of u, which is basically what this rule tells you. It's always the original function, so e to the power of u, this will stay as e to the power of u, so that's e to the power of u, times the derivative of the power, because u is the power, so times the derivative of the power. So this final rule is actually the chain rule. Now what I want to do is just derive the function u, because we know how to derive dy by du, which is just e of u. But du by dx, that's going to be a bit of work. So let's u be equal to this. I'm going to do another substitution. I'm going to use m instead of v, because v and u are easily confused. So m is going to be equal to this. It means that u is equal to m to the power of 2. So now if I want to derive u, so I want to find du by dx. Du by dx is going to be du by dm. Use the laser point. So du by dm, so the derivative of this multiplied by the derivative of this. So I'm using color codes again. Du by dm is just going to be 2m. dm by dx is going to be 12x squared. And then I just undo the substitution, so I'm going to put back the 4x cubed plus 5 and then multiply them together and then simplify. So we go back to here, we put everything we have. This is the derivative of du by dx, this is the derivative of dy by du, and we're going to put it back. I'm just going to bring e to the end because that's what we write by convention. I'm also just going to add an extra step from the previous slide, which is to multiply out the brackets. So we can use rules of derivative to actually differentiate exponentials even further. So if I have this, for example, notice that it's a function multiplied by another function. So we need to use the product rule. So in this case, this is the first term, and then this is the first function multiplied the derivative of the second function. So the second function is e to x, e to the power of 2x, and the derivative of this is just 2e to the power of 2x. And then we do the same thing, the opposite here, and then this is the simplest form. Another example is this. I can say that this is my first function and this is my second function, and I can derive them. So I'll take the original of u times the derivative of the second one, which is negative 3e to the power of negative 3x, and then I'll just continue with the rule. I'll simplify, so what I'm doing is just combining the coefficients, so 2 times negative 3 is negative 6, and then these remain the same, and then this just remains the same. The last rule is the quotient rule. So let's say I have this example, and I'm going to use the quotient rule. So what I'm going to do is have the original, so pause the video and see what I'm doing here. The derivative of the numerator is e of x, and the derivative of the denominator is e of x. So just keep that in mind, that's why I have the e of x's here. And then what I did was I expanded out. One thing to note is when you expand out here, you're adding the powers. So x plus x is going to be 2x. That's something to note. And what I did here, I expanded out, but I kept them in the brackets because I have to deal with this negative. So I didn't want to make a mistake. So then I'll multiply out with the negative. I'm going to get this And then these two cancel each other out, so I'm left with negative 2 e to the power of x divided by e to the power of x minus 1 squared. Hopefully this was clear. It's combining a lot of rules, a lot of different things, but the fluency with using exponentials comes with a lot of practice and understanding which rules to use as well. Start simple and then work your way through the more complex questions.